Good evening, lady and gentlemen. Only one lady here. Thank you very much for your presence here today for the interesting lecture. This one experience one from engineer Indra Jayawardena. June 2016 storm refining critical design condition for breakwaters using measured storm damage. Most of you remember that exactly 1 year back, Engineer Indra was delivered one interesting lecture that's on long wave, something like that one. So today, he will share his experience in Australia on his field on his special coastal these things. First of all, I have to introduce him. Indra Jayawardena, his title is BSc Engineering, MSc, MI Australia, CP Engineer, NPER, I don't know what NPER. He is completing his degree in 1973 from University of Peradeniya. After that, he completed his master's degree in System and Coastal Engineering at the University of Florida. He has 37 years coastal engineering experience in Australia, Sri Lanka, Denmark and Maldives. He has published 35 papers in international proceedings and journals. Engineer Indra initially worked at the Coast Conservation Department and the Lanka Hydraulics Laboratory in Sri Lanka for a period of 11 years, where he personally dived and installed the first offshore wave data measuring was in Colombo, Galle and Trincomalee harbors. Indra has worked as senior engineer at Manly Hydraulic Laboratory for the past 27 years on coastal processes and wave and structure interactions. He has been involved in breakwater assessment numerically and physically, modeling breakwater repair strategies during this period. He was elected to the chair of the Coastal Ocean and Port Engineering Panel of Engineers Australia in 2009 and 2010. He has an advanced diver license and has dived on the coastline of Sri Lanka, Maldives and Australia over the last 45 years. He is very good diver. Just now I got to know that plan in June this year he is coming back to Sri Lanka especially for diving in eastern coast. So he is a very interesting person. So I will call upon to deliver this lecture.
Hi, thanks Engineer Niaz for those kind words. I think you should just consider this as a kind of a discussion. Whenever there's something you feel that you need me to clarify, just stop me and ask whatever you wish. I must warn you, this goes on for about 40-45 minutes and then there's a second presentation. If you want me to stop at the first, I can do that, but I'll just continue on. So just to clarify, the Manly Hydraulics Lab, this is a little incorrect. Last month, the Manly Hydraulics Lab is the oldest laboratory in Australia. It's 71 years old. But just last month, we moved away from the public works, and now the government made us a center of excellence. And so I think it would be easier for us, it will be less bureaucratic and we will be able to work abroad and so on, much easier. Also, I've got to say that there were, this time I'll show you the breakwaters and the coastline, about 2,200 kilometers, but this time after the storm, I had to acknowledge that I went with two young engineers, both whose fathers worked with me in the early 1990s. So they are second generation coastal engineers, Stuart Young and Ben Blumberg. So we can say that in Manly Hydraulics Lab, we have a second generation wave generator, which generates better waves, and hopefully we have second generation DNA, which will design breakwaters better. The third person was Kevin Morton, who actually used the drones for us when we were surveying. I'll talk about that later. This is just a normal day in Manly. This is 5 minutes from my home, and you'll see the level of the water is about 2 meters from this from the wall. And this is, if you'll notice, is a brand new wall. Hope this works out. Yeah. So on the 5th of June, my colleague who now works at the university, who worked with me for 10 years, took these with this video. And this is what happens on the shoreline. If you can imagine on the breakwaters, where wave breaking is much less, the waves are 3 times as high. And I don't know if any of you are familiar with the overtop manual and so on, and there are various requirements for overtopping, like it's unsafe if it's more than 10 liters per meter per second, and it's not good for paved areas if it's over 50, and all this paved area was lifted up during this storm. So you can imagine, if you look carefully, there is this wall here, and you can see a part of it missing. And there was a guy there in front. He went back now. Probably he's a postal engineer. You'll see him a little later on in his car, continuing to video. Okay, let's stop. It will continue. It should have gone on a little bit more, but anyway, we just okay. This is the presentation outline, and what I'll talk about is features of the June storm and brief history of changes to breakwater assessment techniques, functionality and design in the last 2 decades, influence of some storm damage, and the importance of the state of repair of a breakwater. That is, the breakwater can be pretty well conditioned, and it will slowly deteriorate, and suddenly you can have a catastrophic failure. That's the danger. That's the importance of maintaining breakwater. So I'll give you some examples of that. Then I'll talk about the examples of the June 2016 storm damage on crests, heads and trunks, and associated Manly hydraulic slab design models. Some strengths and weaknesses. There were some good successes and there were some failures. So we got to talk about the failures as well, so that we can sort of look into the future. And then I'll talk about modeling repair strategies and design parameters, minimizing the scale effects in models, importance of simulating damage scenarios in models, and some lessons from CERC USA, which has well over 500 structures. So, and then designing for the future. Are models used optimally? I think if there are any modelers here amongst you, you'll definitely say no, they are not, because suddenly whatever the client will suddenly come and say, well, our budget is over, we can't, just as you have set up the model and you think you can do much more with it. So my experience as a modeler is models are rarely used optimally. You're given the brief and you do what you have to, and you could do much more, but time runs out. So finally I'll have some conclusions. So this is when I was in LHI, we had three data buoys, but here we have 7, and we've had them for 4 of them have been over 38 years, and directional data, all of them are directional data buoys now, but with Sydney for 24 years, we have 3 stations, 15 years directional, and altogether 230 station years of wave data. It's about one of the best databases in the world, arguably. They're all in about 80 meters of water. The Sri Lanka one were in about 20 meters of water. So when you're using a numerical model, you can't use it so extensively when it's closer to the shoreline. That's a little bit of the disadvantage we have in Sri Lanka. So this is actually two storms that happened quite close. Notice here the direction is 163 degrees. It's coming from the southeast of the coast. You saw the coastline there. 97% of the storms are from the southeast coast. But the June 7th storm was an unusual one. Now this is the largest wave ever recorded, and that's in 17.7 meters. And this is the aftermath on the shoreline of that same June 6th storm. You can see here there's a swimming pool, and these are very expensive housing, Coleroy Narrabeen. Only about 10 minutes away from the lab, so we have looked at this quite often. So you can see here, if you say, are there anybody from Coast Conservation here? Anybody from Coast Conservation Department? No. Well, the 100 years wave height in Sri Lanka when we were there was about 4.5 meters. Say now it's 5 meters. This is well over 8 meters. So generally the size of a unit is the cube of the wave height. So 5 meters, 125, and then if you say 8 meters to the power 3, about 512, and so you can say that it's about 4 times any unit you use must be about 4 times the size of what we use in Sri Lanka. Now, if you remember, you had those wave data buoys, and this is the storm. You can see how you can track a storm, and this immediately became very big. This is the largest wave ever recorded, and the most noticeable thing is this is 90 degrees here. Most times, 97% of the time, it is 160 to 180. But this storm remained down. That's why the nature of the damage was so different from previous storms. These more statistics it just shows how important it is to collect statistics right down the shoreline. And so the lab has collected all these statistics, and here in Eden, maximum wave is 17.7, and wave periods are generally 12.5 to 15, and useful when you're numerical modeling, because then you know what an extreme wave period is like. And this is the shoreline. And what I have done is marked out some of the breakwaters I'm going to talk about. And we have 63 structures, actually 64, and we are in about 35 locations. And so very unusual. Normally the storm will affect either the north or the middle here or the south. This storm affected all the structures, as you can see, right down the coastline. And this is Ben here. And each storm has its personal losses and traps. And so this lady, Pottsville, is right on the north coast. When we went there to survey the breakwater, she was very upset that her armchair had been moved by the storm. This is the armchair and this is the footstool after 10 years. And here is Ben giving rather unsympathetic ear to her complaint. And then there are successors also. This is Kevin, who does the drones, and in 2014 we named Rock after him because he's also about 125 kilos and he plays prop forward, he doesn't move much. And after the storm, all these other stones moved, but Kevin did not move. So he considered that a personal triumph of his. I'll just give you a brief history of changes to the breakwater assessment. Now this is Rob Jacobs, who's retiring next month after 36 years of work in the lab. And he's not an engineer, he's a science officer. And very meticulous guy. He first did the assessment of the breakwaters in 1993 actually. And he put in all these details. And all he had was this walking wheel, and then 1 year later I joined him, and we used to use a theodolite for all the levels and so on. And compare that to now. This is what we did 3 months ago with 2 young engineers. We have an iPad and everything is on GPS. Life is that much easier. You go around, and when you want, at this point, you click something and you take a photograph, and it's associated to that. So that's our database now for assessment. Again, here's drone pictures. We have drone pictures. Instead of climbing down a breakwater and photographing, we just put the drone and we get it. and these are all damaged photographs of a newly repaired breakwater. Previously, all the breakwaters were damaged on the southwest side, but here we are getting breakwater damage on the ocean side or northeast side because the storm was from the east. So it was an unusual learning curve for us. So this is the kind of assessment underwater. And the three divers we have about 75 years of diving experience. But if you look at their photographs, I've dived occasionally with them, you just can't make out. It's not very useful. And because of their experience, they'll sketch the cross section and give you how it is and so on. But now you can see how technology moves on, and this is the new technology. So here we have got a dual scan sonar, and we mesh it with the digital terrain model from the drones, and we can see almost every rock here. And we can see movement, we can compare it. So that's how easy it has become for the younger engineers. Right. So I'll just give you, this is quite a famous guy called Melby, and he's from Cirque in America, and he just outlined the functional design, plan and profile geometry, wave transmission, overtopping, wave diffraction and reflection, and then filter sizing, armor stability, geotechnical settlement, toe stability, armor unit sizing, armor layer geometry, and armor unit structural capacity. Maintenance strategies and assessment documentation. So what I'll do here is, this is actually, I don't know if you've heard of Stephen Hughes. He wrote sort of the Bible on modeling, on coastal wave and structure modeling. And he was doing his PhD while I was doing my master's in the University of Florida. So when I told Steve I'm going to do a talk at the Institute of Engineers in Australia, he sent me some slides. So I just want to acknowledge him, and I just want to, because it was in fact quite related to our breakwaters, I thought I'd put this up. He says, now I said, you said 265 navigation projects, that's about, if you have two training walls in each navigation project, you'll have 500 structures there. And 40% they breakwater and jetties, 40% originated in the 1800s. It's very similar in Australia, the percentages. That's why I put this up. And the design reality is, majority of existing structures designed and built without even rudimentary design guidance. You'll see why, I'll just talk about it later. And here it is, many structures have survived beyond expected life because of regular maintenance and perhaps some luck. So this is what we've had all through the years. Now we have a sort of as I said, a computerized system and so on, but we maintain good records, and you can see here that actually some of these structures were built in the 19th century. And we sort of, there's an economist who gives us the remaining useful life, and then because it's about a 1.5 billion asset, and we have to maintain it. And then we sort of go and inspect these breakwaters after storms. But when there's a big storm, we inspect the whole coastline. So I've done that on about 4 occasions. Once in the 90s, in 2012, 2014, and then again after the June storm. So this is what actually Cirque or the Americans do. Sorry. So these guys, they have a much more detail. They break the breakwater up, and they not only look at the breakwater, they look at the shoals and the ebb shoals and the harbor shoals. Anybody who did coastal engineering here? There's Hetty, I know. But yeah, so you know, it's important because it sort of influences the structure. You know, all the coastline, all the shoals around the area and on between the training walls influence the structure, so they look at all that. Adapting changes in functionality and adaptive design. See, now you can say it's best to keep the breakwaters very well maintained. But you can see here, this is the Swansea breakwater, a little further south from where it starts. You'll see the stones have not moved at all. A person coming and say, we got to improve this and so on. But it has served its purpose for 20 odd years, and we can see that the stones have not moved at all. This time, now things have got much more efficient. Those days we used to go in a car and we used to go, guys used to take their surfboards and all that. Now they make us go on time. There's a disadvantage in that. We fly to a point, then we use a car, they give us a certain time to do everything. But what happens is sometimes the tides are high, and earlier we would have just hung around and waited for 3 hours and let the water go down and done the assessment. Then we got all these pictures. This time we couldn't do it. The tide is high, we had to finish the breakwater, so we just got a few shots here. But you can just imagine that the stones were just the same. This is a function where it has changed completely. You'll see later. When I first went into this breakwater, this was 2008, I went in 1990. I used to wonder why all these massive stones were used. What a waste of stone. You'll see later on, you don't need to have stone most of the time. Then, when I went in 2012, this huge outlet here has become a narrow outlet. You can see that, like in the Kaluganga, it has got closer to the breakwater. And there is if you look at Kaluganga, you have at what time we had a situation like this. And it got narrower. Then when I went in 2016, it's all sand. So then what has happened here? This is what has happened. So you can see how the past engineers, they used their experience and they built. I was wondering why the rock was huge and whether it was wasted. No, it was not. Because every so 20 or 25 years, there is a breakthrough here and the big waves are hitting this. And here it's all sand. So this part, it's totally protected. So that's what you call change of function in that breakwater. Modeling, simulating accurate storm damage for head repair and head repair strategies. So I just talk about 3 breakwaters, and these you have Coffs Harbour. This is a very probably the most exposed breakwater. We modeled these 3 breakwaters and they were quite successful, so I'll just talk about them. But the last one, we had quite a big failure this time in 2016. So I'm sure there are lots of people here, I know Hetty would be very interested in a bit of maths. These are math, I'm just talking about equations here. Very surprisingly here, this Iribarren almost got it correct in 1938. Hudson was a mathematician, so he used very few variables. And you will wonder how come this is almost still used by all the Americans, and they don't use Vandermeer's. The Europeans use this, but they do the same thing. They get a stability number which should be about below 2.5 for a normal breakwater. But how come this is quite equivalent to this? What Hudson did was, because he was a mathematician, he just used the minimum amount of variables, and all the variables were included in his physical model testing. He changed the water levels and so on, and he got the same, and it's very effective still. While Vandermeer put in all the variables, permeability, you will notice here there's no period. How come you can test without a period? That was by changing the water level and having the waves breaking on the structure. He had this. Now here, he has included the period in this surface humidity parameter and the number of waves and so on and so forth. Right? So that's a very surprising set of equations in engineering, how the same thing is done with entirely very different variables and quite effectively. The Americans partly don't use this because this was done in Vandermeer's PhD thesis using only 8 tests. But it's quite successful. He has modified it slightly over the years, but it's quite successful. But Americans don't like that and they just keep on using Hudson. Okay, how do we apply that? This is one case of Ballina up north where I showed you. This is completely concreted. So as I showed you, the permeability can be taken in various orders, and this is an impermeable breakwater. How do we model that, physically modeling? Well, what I did was we put plastic sheet so that there was no permeability, and then model it. And this is the model. We modeled 360 units and we put 360 units on the structure. And this is a structure which was damaging very often because the impermeable. But for very recently it got damaged, but up for a good 20 years that modeling was successful. And some of the problems here is that you have an interface, what you call an interface, where you have armor units and rock. And armor units and rock, you have to mesh them very carefully. 10% size difference if they are to be successful. But the contractor didn't do that, and this is what happened. On the river side, it was well constructed. On the ocean side, the rock was much smaller than the armor unit, and there was massive damage. But we repaired it in 2015 using big rock, and for the June 13th storm, there was very little damage. So it was quite a successful repair. This is because we were using handbars, and that's an Australian-made unit. Not much testing had been done. So I did this testing to compare it with other units around the world. The Antifer cubes, Acropods, which are very successful. So here is damage, and here is what I call the stability number. You remember 2.5 I said, so you want to stick in this range for your units, and you want to get lower than about 80% damage and so on. But this unit has been very successful. This is what you call a third generation unit. But it is not used in Australia simply because of prejudice. It's a single layer unit and people don't want to use it. So till someone uses it, nobody will use it. It's used elsewhere in the world. I think it's used in one place now. But mostly we use handbars, which is Australian made unit and quite successful. We have tested quite a lot of them. Peter Hanley from our department actually originally designed the unit. And this is a little more description of what you call rocks and comparatively the armor units here. And so do you use Acropods in the harbour Hetty or? Yeah. So you can see Acropods here like the second best. Actually they are the same almost as Pollock. If you notice, these Melby and Turk who got this table, and they are the ones who actually produce the Pollock. So they make it look as if it's much better than Acropod, but all the testing indicates that these are about the same. And these are single layer unit. And you can see here that rock, the number is very low when the stability number is only 2 when when it's no damage. But for severe damage, it's about 2.5 it goes. And you can see that it goes down here and goes up. So there's a range here where it is very susceptible to damage, and that's where the surging and plunging waves are intermingled. That's the transition stage. So that is a very vulnerable stage, and compare that with the Acropods, they do very well here. They are very stable. So that's just trying to compare the different types of units. And this is rock. Rock can be placed quite accurately now. But from recent, when I talked to Steve and some of the guys from SURF, they sent me these photographs about a year ago. This is how we normally use them in Australia. These guys, I show you later the Yakina jetty where they had it was very difficult to repair. It was damaged, massive damage. And they couldn't use concrete units, but they use rock in a very specific way where you have the lengthwise it's placed. The axis is about 2 times the width. Normally you reject such a rock from the quarry, but they used it very effectively and got very high KD values. KD value is, I should have explained that, is a form of how you reduce your armor size. The higher you have a KD value, the lower your armor size. So you can say if it's 3 and this is 9, the armor size here will be 1/3. I don't know if you got that from that equation, but that is the kind of ratio. Using numerical modeling to breakwater. So my first numerical model was in 1996, and I know we use what is called the Miles slope equation, and that's ref-diff, and that is it diffracts the waves quite well. And the surprising thing when I did this modeling was, you notice here it suddenly jumps up at a chain range of 1,100, 200 meters from the head. So they said, well, how can you have that? And I said, well, that's the result we got. We did it and we still got that. So I put it in the report. And then people said, oh, that can't be, that's not a proper result. 20 years later, in 2014, we were inspecting this breakwater, and exactly 200 meters from that was this massive hole. So the waves are getting concentrated there, and it was quite a good explanation of how accurate numerical modeling can be. Uh, and these are not the best models. Now you get what's called the Boussinesq models and so on. But this was slightly less effective than a Boussinesq model, but it did its job, and we quite accurately predicted that. That was one of the successes. And this is just using two different types, the Hudson and the you can notice here the Hudson you get higher armor size than Vandermeer's. Now that was when Vandermeer was pretty early. Now we have learned to use Vandermeer's a bit better, and with the years and with experience. And now if I write this report, this will be a little closer than this difference. So this is now, there are the obvious ones like wave heights and periods and so on. This is what you call the secondary sea state relevant to modeling. You here have wave asymmetry, and you have first and second order wave theories. So I'll show you where we use the second order wave theory. Then there is the shape of the wave spectrum, bimodal spectra, directional spectra. We have now in the lab, we have a directional wave generator, which is, then there's wave grouping effects, and Hilbert transform is related to the actual envelope of a wave time series, which you can then calculate the grouping effect from. And then of course we have the wave incident angle and obliqueness. So this is just an example of how you use second order theory and how useful it is. When we did the modeling, I'll talk to you about the Koff's breakwater. You see these are all interlocked, and we had that these are 28-ton handbars. These are 3 meters high. In the model was about 1:45, small units. They were displaced. And this is where the contractor and the construction and the design engineer and the supervisor have to talk together. And what happened was, I'll come back to this slide. 1 week, I think the supervising contractor fell asleep, or he didn't attend, or he was ill or something. The contractor happily went and replaced these, not like this, but vertically. Over the 500 meters of that breakwater. And so they were very worried. And we said, we didn't want to take any responsibility, this is not what we modeled. So I did a quick calc using what is called stream function theory. And that's what that previous slide showed. That when you use stream function theory, and if anybody is using stream function theory, what you do is, it's not like conoidal theory, it's quite easy to use. It was over about 10-year period, Wiegel developed the tables on conoidal theory. Similarly, a guy called Dean, Robert Dean, developed the tables on stream function theory. And you can see here the stream function theory is the same wave. If you use normal linear wave theory, it's about halfway. Stream function theory shows that the crest is very much bigger. So if you take moments about this point, there is a massive load working on this 20 time. And you can show that it can topple if you keep it vertically. So we wanted to exonerate ourselves. And we said, well, you have built it like this, but it can fall. So, and we left it at that. You can see how big these are. See this band here? They are massive, massive units. And that is it. So this is continuation of the stream function theory. I used it in a different paper to reconcile forces in a physical model with linear theory and second order theory. I use second order theory to reconcile some of the answers we got. So I'm sure if I don't put any equations, there will be a few guys here who will be disappointed. So I just want to show you about stream function theory, Dean, 1974. He was the chairman of our department in the University of Florida. He was essentially a mathematician who later became an engineer. And so you have the Laplace equation, bottom boundary condition. We are saying the velocity, vertical velocity is 0. Then you have what is a kinematic free surface boundary condition, talking about the slope of the wave, and then this is essentially Bernoulli's equation. So, and then what is interesting here is it's almost like Fourier transform analysis, where if you all have done any physical modeling, you will take 50 points in a physical model, unlike in real life where you take 2 points every second. Yeah, so it's quite useful in a physical model. You can use this stream function theory because it's like fitting a curve in just like Fourier transform analysis, and this is just integrating all the velocities to get the force. You're using a CD, which is a coefficient of drag. Now, going on to another aspect, this is wave runner, another design. Very important aspect of breakwater. If you have a very smooth surface, concrete, you get 1. If you have rock, you get almost half that. And you'll see how that affects. And if you have an angle to the wave, no angle, massive amount of runner. If you have just a 60-degree angle, much less. You'll see how that applies. This is all done in the lab first. And this is what you call the Eurotop equations for overtopping. And you can see this is a standard equation. We use that and we try to assess the overtopping. Now these are different standards of overtopping. You can see how different these are. The Japanese are very stringent, and they call this awful. But these guys say 1 to 10 liters per second is quite okay. So this is the latest one, and this is still maintained by the Japanese because a lot of people use their breakwaters for walking. It's like a social platform where people walk around. So this is actually Piank and the European thing. So this is much more liberal, and this is very stringent. So when we design, we generally use this one. Makes life a bit easier. Those days we used to use this. But the actual, now you saw the overtopping in that first video, there's very little, as you can see how difficult it is, prototype measurements of overtopping, very little. There's only Fukuda is supposed to have got it, now recently some others have done it, so it's all laboratory measurements. And this is just about scaling and fruit scaling, you must. And we kind of use 2 methods of mass scaling, Sharp and Cutter and Hudson's. When the prototype armor is, say, basalt 2.6 and we are using very low density armor, we use Sharp and Cutter. Otherwise, we use the Hudson's type of scale. That's all I put it in. This is actually some conditions how you get your scale in a model. And you use certain Reynolds numbers because we don't want laminar effects in the model, and so they suggested about 15 to 20,000, and we base our wave heights on that and we scale it accordingly. So in this case here, because the smallest stone is 3 tons, we have to use a wave height of 3.6 centimeters, and we make sure that there are little, if we use wave heights of about 5 or 6 centimeters, scaling effects are low, so we can guarantee the stability results. So that's how we make sure that our modeling is fairly accurate or quite accurate sometimes. This is actually one of the original studies we did. I just got this from a paper and we tried it. This is normally used, now we use about 4 or 5 methods, directional measurement. That time we are using the Fourier transform method, 4 coefficients, and the accuracy was about 10 degrees. Here, our experiment, it was about 2 degrees. And so it was quite a successful experiment. And you'll see why we did this. It's simply because, you see these are modeling of a breakwater, Foster, which I talked about earlier. It goes down, and as you can see, the wave is 90 degrees here. But as it goes along the edge, 200, 300 meters down, it changes to 60, 70 degrees. And what happens there? What happens is the KD changes. So down at, when it's 60 degrees, 200, you can use stone which is 2.5 times smaller. So it saves an enormous amount. Those days when they did it 100 years ago, they didn't know all that. So they used massive stones. But now with more analysis, we can use smaller stones design. So that was the reason for kind of using oblique wave testing and measuring direction and so on. Function, test design. Now, actually the Department of Lands owns these breakwaters. We used to own them, and they took it over, the department. And in the last 4 years, I must say, they have done a marvelous job. they have now paved all these breakwaters. Regardless of what the condition is here, paved it nicely. And these three generations of the same family using it when we were inspecting the breakwater. There was a humpback whale on this side and a dolphin jumped out of the water 8 times on this side. So people come by their hundreds and use it socially, particularly in the small, in the small towns where they have not much recreation and all that. People use these, and so it can be in Sri Lanka also. You can, if you pave your breakwaters and so on and so forth, it can be a real social venue. You have people running along these, cycling, and here you have a disabled person coming along. So it's kind of a very useful thing, social part of the social life of a small town. This is how this was in 2011, and now the Department of Lands has improved it, and you will see how improved it is. But one thing, if you notice, the fishermen are exactly in the same spots, and there's one lady fishing here and there's one lady fishing here. So that's a strange coincidence. And this is the RTK. This is our device which we measure. We can get levels from satellite surveys, the GPS system. This is a big error we made. We repaired this breakwater about a year ago, and this is the longest breakwater, 1.5 kilometers long. We repaired it, and after the storm, we had 400 meters of crest damage. Here it is. So why was that? It's simply because, can you remember I said when there's concrete, the friction factor is 1. When you have the armor, two-layer armor, friction factor is about 0.55, half. And because in those days the repair machinery was not so good, they dumped it. Of course, you had to pay more to the contractors because but there was a lot of, this is not the best example, there are examples of where it is very high friction. But with better machinery and the contractors wanting to use less stone, they smoothen this out quite a lot. As a result, what happens is the waves run up much more and the crest gets damaged. So those are some of the pros and cons of using modern day machinery and very good reachers and so on. This is the same breakwater, 2008, damage on the crest. 2014, repair. 2016, again after the storm, damage. So we went and surveyed this. They're not going to do anything else. They're not going to, it's most convenient for them to just repair this again. And then they let it damage. Because lots of people use it. The next best thing is to actually, show you, put a berm in or raise the crest, very expensive solution. So what they do is they just repair this again and go on. So that's about functionality and so on, and expensive. Here again, Cloudy Head Harbour, after the storm, massive crest damage. That's me taking a photograph there. So here's Wollongong. Now we're going south, further down south for those time. Massive wave overtopping at this breakwater. It was quite damaged. We are making some CADs for climate change here. And you can see how big the influence of climate change is. We at 90 centimeters, and we do a numerical model, and it's a massive effect on the overtopping of those breakwaters. So something to think about in future. These are all the breakwaters we have. Now this is a sort of a solution for high wave runoff, putting in a berm. So this is one of the physical models I had done, and what it showed was when you put in the berm, there's very little overtopping. But it is an expensive solution. But there are places where it is necessary, where it's so dangerous. I'll show you something. Now this is a berm, only berm I could find in the 68 breakwater. I don't know how it came there. There is no history of it. This is in Naruma, and we are doing a assessment now. Here the crest was not damaged. Like in the previous one I showed you, the crest was damaged, and this is just the breakwater next to that breakwater where the crest was damaged. The crest was not damaged simply because of this berm. And I don't know how the berm was. Probably it was much lower breakwater. This was the head, and they extended the breakwater, and they just kept the original head this way and made this. And so there is a natural berm there. which prevented overtopping and safeguarded the breakwater damage. This is actually modern. This guy actually was involved in the Hambantota design of the breakwaters. And I keep in touch with him. I worked with him 3 years ago, and he sent me his paper on Hambantota breakwater design. And he's kind of what you call, he's from Iceland, and he's expert on Icelandic breakwater. So we are now, this is a model we did about 3 months ago, and we saved on about 10 million. And we are now using what is called berm design and so on for getting better berms and designing them. Here's a place where a berm is necessary. There's a beautiful island on this end, and people keep walking through during storms. Can you see the storm is going? This guy is happily walking through. And these are kind of rocks that go through. There were two massive rocks which went this storm, which actually hurt 2 of these boats, and they went down into the water. So these are very dangerous place. Now what the department has done is they put a gate across, and we forecast the waves, and we say probably there will be northeasterly waves, and we lock the gates to prevent people from going for safety reasons. Simulating accurate storm damage is very important for breakwater design. So here we are. This is the Foster breakwater which I talked to you about. Every 3 years we had to do $200,000 worth of repair. We said, come on, let's do a model. They said, no, we'll just repair it again. They repaired it again, and for a small wave height, only 4.5 meters, it really got damaged. Then they asked us to do a model, and we did the model. And we showed that 8-ton army units get damaged quite badly, but 11 tons is quite good. And that's it. This is putting in the 11-ton handbars in. And this is the final result. And we had 5 storms, some of it well over 4.5, and very little damage to the breakwater. But, I told you about the state of a breakwater. Now, as time went by, that was the first year, 6 big storms, nothing happened. Slowly it started damage, and we didn't repair it. This is damaged 2006, May 2009 storm. This is what is called a 1 in 40 year storm, quite a big storm. And this is what happened in the June 2016. Because we were just about to repair it, we had collected all the armor units. It was at the site just before repair. The storm started, and this is massive damage here. Here, this area is 0 coverage, very big damage, which could have been prevented if we had just done the repair 3 or 4 months before. But so that's the importance of repair. Simulating accurate wave and current interactions. Now, we've never actually simulated current and wave. We just have modeled our breakwater design with waves. So when I talked to Steve about it, he said they also did most of the time they did it, and they did it for this in 1978. They spent $8 million and repaired this. But in 1988, there was 40,000 rocks which were displaced. So you can imagine, it's like, how much? 2,000, 20-ton rocks, which were displaced on this head. Like 200 meters was lost. And they couldn't explain why. They had done an extensive model, and nothing had, there was no damage on the model, no damage on the model. But in real life, it got damaged. They had very good wave data. They couldn't explain it. They got guys like Dean, my prof, and some others together and said, why is this? They said, why don't you try doing the current and wave interaction? And that's what they did. And subsequently, they modeled it. And remember, I put in those stones at KD8 and so on. They didn't use concrete armor. They used these stones, and for the last 8 years, very little damage. So for each place, you have to sort of consider what the interactions are, what is special about that location. You just can't go ahead and use one kind of solution for all. And this is one of the most vulnerable breakwaters, Hoff's breakwater. And we modeled this. This in May 1997, a very small storm, a 1 in 1 year storm came over. And what happened? 12 armor units, not 2,000, were removed on one night. And these are the armor units. These are big units. 12 armor units just in one night. And this is because the wave height and the water level coincided. Very high waves and very high tides. That is one of the reasons. And you can see here, this also, the wave direction was east-southeast. It was much more easterly than the normal waves. And it changed suddenly. And you had big repairs. The wave height and the water level coincided. This is a numerical model, and what it shows here is a 1 in 100 year wave. 1 in 100 year wave breaks offshore. That's why a much smaller wave, when you numerical model, it breaks here. So much more damaging. We design with 1 in 100 years, but they may not be the worst conditions. So this is a 1 in 1 year wave can be the worst condition as it was there. So that's why sometimes when you're modeling, you might do a model for a 1 in 100 year wave. But I asked that question, do we use models optimally? And sometimes the client is satisfied that we have done a 1 in 100 year wave, modeled it. But it may not be the worst condition. So the ideal thing is for the engineer to reduce the wave height and see if it really breaks on the breakwater. And see much smaller wave height offshore can be much more damaging to a breakwater. Similarly, the direction, slight changes in direction can be very damaging. This is the so we can't now at that stage in 1990s we couldn't model what was under the water, like I showed you. So here we just modeled the damage above water, and it was a very successful repair. We put in these 28-ton armor units there. Just getting this crane here up here was $90,000. Then 2 weeks after that, everything was washed away, and we had to spend another $90,000. It was such a vulnerable breakwater. And this is the storm that hit it subsequently, 5 or 6 years later. And this was a 1 in 40 year storm, and this is a very big wave. These are, like I showed you, these are 3 meters. So the waves are going right over them, massive waves, all along the length of the breakwater. And here's the damage on the head. Just 1 unit moved. So our modeling was quite good. We were quite confident about the model because we had replicated, quite a lot of the conditions, and we had modeled it. But what happens next year? A consultant comes in 2013 and says, you got to armor this side with 4,000 handbars. Each handbar is about $5,000. And also the same with this side. And he gives a bill to the Department of Land. Now, because we were speaking for the government, we said, no way. We have inspected this breakwater over 20 years. We have seen it after the 2009 storm. It didn't damage that much. Why would you want to put all this? So we had a big meeting. And I said, we'll model this. They were going to construct. I said, we'll model this in 1 year, 1 month. And we spent Saturdays and Sundays being a government organization with the 3 young guys, and we modeled this. And we didn't have what the designers had here. We didn't put additional armor on the head. We only had these additional armor here, and we modeled it. And you can see the model here. This is our directional wave generator. And so they wanted it done quickly. Every single unit was placed exactly as it was in nature. This is an aerial photograph, and this is the model. Every single unit, if you look at this, see this is placed exactly as this is in real life, just like that. So we need quite careful. And we of course couldn't simulate the exact damage to the 2009 storm. There 1 unit had moved, but we got only 1 or 2 units moving. So the actual storm unit from here moved, but here we have 1 unit from here moving. So it was quite good simulation of what actually happened. And this is again modeling that. Here's you can see our directional wave generator here, and we can move and wave. It's like a new generation from the old type of wave generator. Very useful. And these is all 3 to 5 ton rock. Instead of spending $5,000 for each for 3,000 odd units, just 1 to 3 ton rock. And here are the results. Here again, like I showed you earlier, 1 unit moved. And then there, unfortunately for us, 5 storms hit that breakwater soon after it was constructed. 5 storms. And this is the last storm, 2016, and this was the result. For the first 5 storms, this was the most damage we saw noticed. And on the harbour side, there was a little bit of crest damage. Other than that, there was very little. And so, instead of spending 37 million, the government spent 20 million less. This is after 2016 storm. There's 1 unit here and 1 at the crest which had moved. It's got 28 hands. And this is what was read out in Hansard. And it says here that MHL saved the government 25 million. Actually, we kind of considered it only to be 20 million, but we didn't say much because the government said it was 25 million. We just let it be. But this is the Hansard publication on the day. And these are some of the conclusions. So here we say physical modeling in conjunction with numerical modeling has provided an invaluable tool to select site-specific design storms and optimize repair strategies. Replication storm damage in the model proved to be useful after the May 1997 storm and the May 2009 storm. In the Yakina jetty repair, simulating wave and current interactions was important. None of our models we didn't simulate both currents and waves. Ongoing monitoring and concrete testing of the armor units, updating MHL's extensive database, particularly after extreme storms, ensured the primary armor units maintain the integrity of repair. Timing of the breakwater repair proved to be important for the Foster breakwater. The June 2016 storm, although not extreme, provided pointers to where future strategies for repair and maintenance could be improved. Thank you. And this is a guy we really have a lot of faith in. He has a lot of faith in our design. Here is a fisherman who was there in a massive storm and he thought our breakwater will hold. So I put his picture in. Any question? Just fire away. No. Yes, Eti? Okay. Yeah. Okay. Right. Yeah. So as you said, those are very high, very high KD values. But would you know the armor size? Because I thought they were sort of oversized, or different sizes. Right on the head, how much is it about? 22 tons. Yes, that seems very huge, very big to me. But still, yeah, they'll be like the pharaohs, when in 2,000 years from now they'll still be standing like the pharaohs' structures. Anyway, so that's that one. You could, please feel free. Are there any other questions? What we can do is, if you want to stay on, I can just do a 20-minute presentation on the on a estuarine problem, which was quite unique. And is it okay if I do that, or I can stop now? This was a presentation I did for the Coastal Conference in New South Wales in November this year, and it had a unique feature which I thought was useful to share. So this is called investigating strategies to repair historic tide walls on the Clarence River, Whiting Beach and riverbank protection. So my co-authors were Andrew Hartley from the Department of Lands, Ben Blumberg, who is in our department, and Ed Curiel, who is the director of our laboratory. So brief history of area and recent problems, outcomes of field trip and bathymetric survey, results of a Mike 21 SW wave modeling, design guidance for tidal wall repairs, utilizing a physical model, strategies for future consideration. So this is where polyswarm. This was the long, remember? Sorry. So remember I talked about the 1.4 kilometer wall, that is this North Clarence. And this is the estuary associated with it. And Collis Wall is here. It was built in the 19th century. Similarly here the Middle Wall. And these are important areas because the town is getting bigger and a lot of people use this. So that's why the walls are deteriorating. So they asked us to investigate. So like I said, the structure started in 1893 here. And this is the Middle Wall. And this is again Collis Wall, and this has various structures on it. You know, here we have the channel beacons, then you have the harbor beacons and so on and so forth. You'll see what is happening to them as the wall deteriorates. So this is the wall itself, Collis Wall. And what is unique is made of very small stone. And you'll see that very small stone, 10 kilograms. But how do we design for this? Now can we use breakwater methodology? No, the answer is no. This has been fused together for years and centuries. Might have broken. Those days they might have maintained it, but they haven't maintained it for the last 40 years. So it was a bit of a quandary. There's not much history in the repair. How do we repair things like this, which is deteriorated? And we can see here in 1995, Collis Wall was attached to Goodwood Island here. Aerial photograph. 2005, it is no more attached. So during those 10 years, conditions have deteriorated steadily. And what happens then? You get massive erosion on the river banks, massive loss of land. Here, these guys, only house which is around in that area, they have built their own riverfront and so on and safeguarding their place. But go further down and you get massive erosion. Further down and you get huge erosion. These are the beacons almost falling into the water. This was on land at one stage. So it's a very serious situation for the harbour, because harbour has sort of reduced in size. Those days it was a big harbour with timber and so on being transported, but still quite a few big ships still go up and down the river. And we have water level recorders and water quality recorders in about 400 stations on the coastline. We have one here, and you can see here that there have been storms and floods, but in the last 5 years there have been quite a few. The frequency has got increased, and these floods actually, we don't measure the velocities, but there is estimated to about 5 to 6 meters per second. So how do you design a wall for 5 to 6 meter flow rates? Quite unusual situation. So this is actually the bathymetry, and you can see here there are massive sand waves. These slowly reduce with time, but these are caused by the floods, not by the ebb and flood tide. And this is going up to 12 meters here near the wall. And the wall is falling into these holes, it's deteriorating. This whole riverbank is now eroding at a big rate, massive loss of land. So it was a big problem for the harbour master. So this is one of the reasons. We really looked into the history and we found that there was dredging done here in those days. And what they used to do was they used to put the dredge on the other side of the wall. So they used to reinforce that wall, that area. It was connected. But as time went on, you couldn't put dredge material because of ecological concerns on land itself. You had to put it offshore. So they started putting it here. So the land side of the walls were getting neglected and the walls were falling down. So here the wall, the middle wall, there was a train line which went on this. These for the train line, and these are about 3-ton rock here. And this is also getting deteriorating. And what is happening there? Massive erosion on the banks, and huge erosion because that wall has been going down. Now the mean level of that wall is just about 50 centimeters higher than the highest tide, and of Collis Wall it's about at mean sea level, and so it's a big problem. And there's a lot of development on this side. This town is growing. Clarence is a big town. So what we did was we ran a numerical model, we did the SW. We had the BW model, but we didn't run it because we didn't have money for that. And also a lot of wave breaking here, so we ran the SW model of the Mike 21. And here, what we used as boundary conditions were the boundary conditions we used for the, I told you the one design of the 1.4 kilometer breakwater. We had run it up to about somewhere here. So we very conveniently for the 100-year wave, we used this boundary condition. And these were the boundary conditions. And that's how you can use one model after another. So when you're using one model, always got to think, how can I best use it in another model? And here we are using it in an entirely different model. So we looked at the waves that come down this. And we looked at Whiting Beach as well, which is eroding, as I showed you. And we put in a little drawing here to see what the influence of that of that drawing is on the waves and their direction. Most importantly, on the direction. So if you know about longshore transport, if the waves are perpendicular, there's less longshore transport. If they are at an angle, you get more. And we put a second 100-meter T-wall. There's a little bit here from some old, we don't know the history of that, old construction, so we thought we can extend that. And so those were the two options we tried in our model. And we got some, so this was, we simulated currents as well. Because Manly Hydraulics Lab had taken tidal currents there over 20 years, we knew that the currents were about, at the maximum were about 1.4 meters. So we ran a 0.7 meter current here and 100-year wave conditions. We thought that would be sufficient. And we got about a meter wave height at the head of middle wall. At Colliswall it was very, very small, less than 10 centimeters. So we were really not worried about the waves at Colliswall, but we were certainly worried about the waves at middle wall. But remember I told you there can be 6 meters per second or 5 meters per second currents there. Similarly, when we raise the waves and currents, we got quite sensible results. That is, when there is no tide, in the flood tide and the ebb tide, we just got a very reasonable result from an engineering sense of that. But you can see here the direction changes here. So with the wall and with no wall, there is a change in direction. It just gets more oblique here, and so less longshore currents when there is a 200-meter T-wall. So that is a solution, because now you're having less longshore transport and reduced wave heights also. Reduced wave heights, remember we had 0.95, now these are much reduced from that. And this is the wall I told you where we are going to start it. But we had a lot of government restrictions, we had to get permission here. So because we were losing beach, what Dance did was they nourished the beach. Now the ideal thing would be to monitor this very carefully so that you get a theoretical understanding of it. But they haven't done that. But still the beach is surviving. They have missed a glorious opportunity to monitor it. But hopefully, I was talking to the engineer there, Andy, I worked with him. He was one of the co-authors. So that's what he intends to do. And this is Colliswall. This is just how are we going to repair Colliswall. Much smaller armor, as I say. We have taken the cross sections, and what the real unknown was the currents. So what we did was we used current modeling from a previous model, and this I haven't seen it done before, and it is based on the PN guidelines for berthing structures. We had used it in the a port engineering organization had asked us to build a rock mount as a brake to a braking ship, because in Fremantle, one of the ships, when there was a meteor tsunami, that is a tsunami caused by meteoritic conditions, it went and struck the bridge in Fremantle, and the city lost electricity for 3 days. So what they came to us and said, hey, build us a brake and build us a rock mount structure to prevent such a thing happening. So we used that modeling to repair these. We modeled that with 5 to 6 meter currents. So this is that model. In the flume, we are looking at 5 to 6 meter currents which we normally don't use, and we are looking, this is a ADV, acoustic Doppler current meter, measuring it right around the rock mount and the breakwater. So we got some experience. We measured it in 2-dimension and 3-dimension. These were jets from thrusters which they want to prevent the rock mount being damaged. So these jets are 6 meters per second, very similar to the currents from the floods. And so we had some experience of high currents, and we used that, and we said, okay, because we had used the theoretical variation in the jet, we try to match that in real life. We got a fairly good match. So if you notice here, they go up to more than 5 meters per second, 2 jets coming onto the structure. In a sense, we had massive currents on the structure, and there was very little damage. There was a little damage. When you use basalt, there was no damage. But this is slightly lower density rock and sandstone, and there was damage. So it was sort of optimized that way. And this is, we designed these to connect two options to connect Coliswall to the Goodwood Island. One a long option here, more expensive, one a short option. So then you might lose this part of this amount of land. So you have to weigh the consequences. And so these are the suggested criteria. Do nothing option, which was not an option, too expensive. Then you had a pile support option just for the navigation markers I showed you. Do nothing. That also, in my mind, is not an option. But then we had to put a scour blanket on Coliswall because it was getting loaded, and then repair the western and southern end of Coliswall with small rock. And then here we have connect Coliswall to Goodwood Island and fill the gap between the land and the mast. Remember, I told you they took the dredge material out and put it offshore. They're saying put that material in again, and so that's another option. And then protection for Goodwood Island, 2 options. First, cut off flow between Coliswall and Goodwood Island, and the other more expensive option would be for the practice of homeowners on the island living in close proximity and build a revetment structure. And then middle wall, it's best to use about 3-ton rock and build a 220-meter groin, as we showed, and then nourish the Whiting Beach as well. Thanks. Any questions? Good. Thank you. Thanks.
Our audience very less today, because the one reason was we expect more Ports Authority engineers, but our committee member, Engineer Ganegoda's father, expired, and his funeral today. Because of that, Ports Authority engineers also left, and our committee members also, including our secretary. So because of that, this less crowd today. Very sorry for that one. Anyhow, we have a crowd. So first of all, I have to thank all of you. Before that one, we have one token of appreciation to our lecturer today. Please, I will call upon Engineer Hudson from RDA to hand over that one.
Thank you very much. Thank you.
Again, thanks for all of you to be here until the presentation over. This is our 3rd lecture on the Civil Engineering Sectional Committee. We will continue this momentum on every month. So please, I am inviting all of you to participate our lectures in the future. Thank you very much.